All right, it's about time. Welcome back, everyone, and welcome to the storage session. So storage is for interesting people. I'm really glad to see you here. In this session, we have 6 presentations, including 2 remote presentations. And the first presentation is given by Junyi from PKU. So Junyi is a second-year PhD student at PKU, and his research interests lie in building disaggregated storage systems atop modern networking and storage hardware. Okay, so Junyi, take it away.
Okay, thanks. Hi everyone, I'm Junyi Shu from Peking University. Today I will talk about our work, DRAID, which allows you to build a scalable and reliable block device with disaggregated storage. So modern data center fabric is evolving towards higher bandwidth and lower latency. So different components in a computer used to be interconnected with local bus. Now we can also access a remote device with enough bandwidth and acceptable latency. Disaggregated storage becomes popular in cloud data centers. It decouples resources into diskless compute clusters and storage clusters with limited compute power. It is very attractive to both cloud platforms and their users because compute and storage can now scale independently, which leads to higher resource utilization and lower cost. On the other hand, redundant array of independent disks, especially parity-based RAID, is a key building block for realizing a virtual block device with bandwidth and capacity beyond what a single drive can offer. It also achieves high reliability by storing actual parity chunks. However, it is a well-known problem that partial struct write and data reconstruction of parity-based RAID can lead to severe I/O amplification. There are basically 2 approaches we can do to build RAID over disaggregated storage. One is to disaggregate the RAID controller to a storage server and uses drives from the same machine. The other is to decouple the RAID controller and the drives. Let's consider a single drive failure. For the single machine approach, you have to find another available drive on the same server. But for the decoupled approach, you can use any drive from the entire storage pool. As for a server failure, if you take the single machine approach, the entire array becomes unavailable to client, and you may lose the data forever. But if you carefully choose the member drives for the decoupled approach, your array is still available, and the data can be reconstructed from other drives. So for these 2 reasons, we believe the decoupled approach is preferred in a lot of cases. So, but how I/O amplification impacts a disaggregated RAID? Assume we have a RAID 5 array with 8 drives. The parity chunk is basically the sum of the data chunks in the same stripe. We first look at data reconstruction. For a normal RAID I/O, we only need to touch 1 chunk. But if chunk C4 here becomes unavailable, we have to read all the other chunks to reconstruct C4, which creates 7 times amplification. For partial struct write, say we only update C4 to C4 prime in a stripe. A naive approach is to retrieve the unmodified chunks and recalculate the parity. Then we update C4 prime and CP prime. A smart way here in practice is to retrieve C4 and CP instead. You can derive CP prime from that. In total, it requires 2 reads and 2 writes, which incurs 4 times amplification. It is still a problem because the amplified I/Os all go through the host NIC. So we can do some simple math here to see why this becomes a problem. Let's assume we have a 100 Gbps NIC on the host. An enterprise-grade NVMe SSD provides more than 16 Gbps write and 24 Gbps read bandwidth. If we use each drive separately and have no I/O amplification, the NIC can saturate bandwidth about 4 SSDs. Recall partial struct write can trigger 2 writes and 2 read and 2 writes That pretty much means half of the write traffic will occupy the entire NIC. The write traffic, and things could be worse for data reconstruction on a large array. So where do the actual network IOs come from? The source of actual IOs is a centralized RAID controller. It does everything except the drive IO processing. So the key idea here is to decompose the controller. The formula to calculate CP prime here can be expressed in a different way. We first calculate C4 prime minus C4. Then we add CP on top of that. We now have CP prime and we possess it. The calculations are in place at each remote target, so the network overhead is minimized. To apply this idea to the real world, we ask ourselves 3 questions. What architecture change do we need to make? What protocol changes do we need to make? And how do we design the system to maximize the parallelism? We'll answer them in the next few slides. So here, every data access between servers must go through the host. To enable peer-to-peer data access, we must create a connection between each pair of the servers. The host controller exposes a user interface and orchestrates each read and write workflow. In contrast, the server component does whatever the host asks it to do, including parity calculation and the data transfer. But how does the host control the behaviors of the server controllers? NVMe-OF is a widely used disaggregated storage protocol, but NVMe-OF only supports a few basic commands such as read and write. We create DREAD protocol by extending NVMe-OF protocol. It supports host-to-server commands and also peer command between servers. It includes necessary parameters for these commands, and it supports both RAID 5 and RAID 6. Now let's see how DREAD uses the protocol to support partial struct write. Here we want to update D1 to D1 prime, D2 to D2 prime. We can conceptually divide the workflow into 3 phases. In broadcast phase, we first send commands to the involved servers. Upon receiving the commands, data servers fetch the new data, and parity server retrieves the old parity. Data server also needs to retrieve its old data. Now each data server can calculate the partial parity and then possess the new data. In reduced phase, each data server notifies parity server with the peer command, which lets parity server fetch the partial parity and eventually generate a new parity and possess it. The last step is to notify the host the final result. The problem here is the entire reduced phase relies on the parity command to arrive first and provide necessary parameters, such as how many partial parities are expected and is it required to retrieve the old parity. If it arrives late, reduced phase is blocked. So an easy way to address this problem is to use a barrier which we try to avoid when possible. Parity reduction is basically addition and subtraction, which does not require a specific order. So what we can do is we can just allow the reduced phase to proceed and only make sure parity command has arrived before we process the new parity. We'll have a few available buffers on parity server. We can keep reducing the partial parities, and we eventually see the parity command. And now we know we are waiting for 2 partial parities, and they are all here, so we are done here. Non-blocking multi-stage write allows more parallelism across servers, but there are opportunities also within a node. Modern NICs and NVMe SSDs can support many concurrent IOs, which we should take advantage of. This is execution workflow of NVMe OF write. Each action depends on the previous one. But for DREAD partial struct write, the dependency graph suggests there is an opportunity to parallelize the actions across the devices. So why not we pipeline them? We take advantage of this unique opportunity and apply pipeline parallelism. We enqueue the IOs to NVMe SSD or NIC as soon as possible and let them do the rest for us. And don't forget, another source of IO amplification is data reconstruction. A straightforward approach is to randomly select a reducer to reconstruct the data for the host every time. But it does not work well when each server has different available bandwidths at a time, which is a reality. What we want to do is to balance the available bandwidths. So a better way here to do is to choose a reducer based on probability calculated from current available bandwidths. We implemented D-rate on top of SPDK, a user space storage framework. We use the publicly available platform Cloud Lab as the testbed. We examined node scalability of D-rate. OR, it is linearly scalable. For write scalability, D-rate shows very consistent latency and scales towards the need good put. For degraded rate, D-rate is very close to normal state rate, while SPDK becomes overwhelmed due to host NIC congestion. If we only have reconstruction, SPDK becomes even worse. D-rate also scales with number of concurrent IOs. D-rate outperforms SPDK by 2 times on write-only workload and 3 times on read-write workload. This is very close to the theoretical improvement. We implemented a lightweight key-value store and run YCSB against it. On the normal state, improvement of D-rate is mostly on write-heavy workloads, YCSB A and F. And the improvement is more significant on the degraded state across all workloads because D-rate improves both read and write. For more experimental results, please read our paper. So to conclude, D-rate is a disaggregated software-based read system. It exploits peer-to-peer disaggregated data access to reduce network usage and applies system techniques targeting modern hardware to maximize parallelism. We show that D-rate is scalable and provides up to 3 times overall bandwidth improvement. Thanks for listening, and I'm ready to take any questions.